Okay, guys, please don't cry. The real world application for this is actually used, I want to say you guys end up using this in physics, but you definitely use it when you're in engineering. And so this last example is just taking this concept of real and imaginary numbers, and it is talking about kind of applying this to electrical circuits. So the table they've given you, all they're telling you is that if this is the symbol, okay, then we're just going to leave whatever the number is, whatever the number they gave us for it, is just going to be left as a real number. If it has this symbol, it's rotated 90 degrees, and what this means is that we're going to end up with an I at the end of it, but it's going to be a positive number. If we have this symbol, it's rotated a negative 90 degrees, so we'll have an I, but it will also have a negative number in front of the I. And so what they've done is they've drawn you a fun picture, okay? And then they have given you, I'm going to try to scoot this over a little bit. Then what they've done is they've kind of done a lot of the work for you. So if you look, we have the little squigglies and a 4. So that was just a real number. So that's why the impedance is 4, because we know that it's just a real number, there's no imaginaries, and it's positive. Okay? Then the next symbol is these little squiggly lines. Okay? So the little squiggly lines told us it's an imaginary number, but we're going to leave that positive. So that's a 3, but it ends up being a 3i because we needed the imaginary number involved. Then the last symbol we have is those sticks things, just like this one right here. We knew that we're going to turn that number negative and it's imaginary. So we turn the 5 into a negative 5i. So what they've talked about is it wants to know what is the total impedance for the given circuit. So all they did was they take the 3 parts and they added them together to get this complex number. So for part B, what it is talking about is it talks about using Ohm's law to find the voltage, okay? And what this is asking us to do at the end is find the voltage for each component. So here's the impedance for each one, and they've given us the I. So, the Z is the impedance for part 1. So the formula is V equals I times Z. They've given us I. We're going to pull, each of these is going to be a Z for a different part. So if we flip it over, they've walked us through doing that. Okay, so it says voltage for the resistor is I times Z. Well, this is I. We have to go back, and what was the Z? So the Z for the resistor was 4. So I'm going to plug in a 4. And it should work out 24 times 4. Well, 4 times 4 is 16, carry a 1. 4 times 2 is 8, plus 1 is 9, 96. They got that. And then we need to distribute the 4 to the 12 I's. So that's a positive 48 I's. Okay. Then we need to find the inductor. So we're going to flip it back over. And for the inductor, we had a 3I. So that's what I'm going to plug in, 3I. And I am going to multiply. So 3I times 24, ooh, they ended up with a negative 36. So I might do all of this by hand and then plug it in. So if I times 24 times 3I, that is 12, 672 I's. And then I end up with plus 36I squared. Oh, I see now. So I squared is a negative 1, right? So negative 1 times 36 is that negative 36. So my answer has to be negative 36 plus the 72 I's that we found. I have a feeling this is going to end up similar on the other end. Let's double check it. So we need capacitor. That's a negative 5I. So we're going to plug it in, negative 5I. Okay. We're going to multiply. 5 times 24 is 0, 10, 120 I's, and it's negative because negative 5 times positive 24. And then we have a minus 60I squared. So we know that the negative 20I does not simplify. It ended up back over here. But negative 60 times my I squared. Remember, I squared is really a negative 1. So that turns it into a positive 60. And then I want to know, what is the sum of all of these? I know we don't normally do the reflex, but I'm curious to see what this says. So find the sum, which means I'm going to add up all these things. So 96 plus 48i minus 36 plus 72i plus 60 minus 120i. So if I take all of these parts, well, 96 minus 36 is 60. And 60 plus 60, we end up with 120. 48 and 72 is 120i, and that's a negative 120i. So we ended up with plus 120i minus 120i. So those cancel. We end up with 120. And guys, look back over here. The voltage for the circuit was 120. Okay, that's pretty awesome. So 13, let's try to work this out ourselves. Suppose the circuit analyzed before had a second resistor with an impedance of 2 ohms added to it. Find the total impedance, given that the circuit now has a current of 18 plus 6i amps. Also find the voltage for each component in the circuit. Okay, so we need 2 resistors, an inductor, and a capacitor. So we have an R1 and R2, okay, an inductor and a capacitor. So first, let's just find the Z's. So we should still have a 4, a 3i, and a negative 5i, but we've now added another resistor with a 2. And they've given us a new current of 18 plus 6i. So we have to multiply across and then add and see what we end up with. 4 times 18. 4 times 18. 72. 4 times 6 is a positive 24i. 2 times 18 is 36. 2 times 6 is a positive 12i. 3i times 18. 3 times 18. 54i. 3i times 6i is a positive 18i squared. Okay, which is really a negative 1. So we have 54i minus 18. Negative 5 times 18. It's negative 60 i's. Negative 5 times positive 6 is a negative 30 I squared. Again, I squared becomes a negative 1. So this is like saying negative 60i plus 30. And let's just see how it works. So if we take the 72, the 36, the negative 18, and the 30, what do we get? So 72 plus 36 minus 18 plus 30, we end up with 120. And what about the i's? We have 24 plus 12 plus 54 minus 60. 30i. Did we do something right? Yes. 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 Oh, 5 times 18 is not 60. 5 times 18 should have been 90. Okay. Let's try that again. 24 plus 12 plus 54 minus 90. Ah, there we go. Plus 0i, which canceled, and we get the 120. Miss Blunt can make mistakes. It's okay. So that is all the examples for 4-2.